And then we will start a lab tour.
Hello, I'm John Levy, the CEO of SEEQ. Today we're going to walk around and we're going to see how we design chips, how we manufacture them, how we test them, how we integrate them, and in fact how we integrate them into a full quantum computer that we're seeing right here.
As you can see, the chip design itself essentially comes down to a CAD drawing, or like what looks like a piece of artwork where it's just shapes. And these shapes all represent metals or other films that end up being deposited onto a substrate. So this is a centimeter by a centimeter. And so in this tool, I can design, or I can draw different shapes and the different layers that they physically appear on the chip. So most of our chips consist of several chips. So a bottom chip and a top chip. Here they are superimposed on each other. Here are all of the metallizations that are on the bottom chip, the carrier chip. And then there's a second chip that contains the qubits. So here, this is the quantum chip, and it's this much smaller chip here. And all this contains is qubits and their associated readout resonators, which are these little windy lines here. And then this chip gets bonded on top of the carrier chip to make the total device. So the carrier chip, this gets fabbed in-house in our own fab. And then the flip chips we order from a quantum foundry. And then we receive these chips and bond them together to make these MCMs. And this is what we're currently measuring. So because it's modular, it means that we can verify the functionality of the most complicated stuff before we actually take the time to assemble and potentially sacrifice a flip chip. So we can take just this bottom chip, test it at 4K, and verify that it's functioning, and then we can go and make a bond and actually make an MCM, and then we can proceed further with the testing. I do physics simulations and circuit simulations to find the target circuit parameters, but then you have to make a physical shape that gives you the correct circuit parameter. And to do that takes a lot of creativity, because there's kind of infinite solutions to that problem. So you can make any number of shapes that give you the right electrical characteristic. And so it's kind of like your own thumbprint on the design, because you made it look a certain way, even though there was probably 1,000 solutions that would have done the same thing.
So here we have our measurements lab. This is where we can figure out the thicknesses of some of our chips for some of the layers of metal or insulators. So we have different equipment with lasers and sensing technology. We can figure out stress on our wafers, uniformity, things like that. Hi, I'm Asa Chamble Jacobs, and I'm a facilities and equipment engineer.
What does that mean?
That means I try to keep all of this stuff running. This here is a sputtering machine, which we use to deposit our niobium, our aluminum manganese, and our molybdenum. So a lot of our wires are actually made of niobium because it superconducts at low temperature. So in here, you can load wafers onto a pallet that looks like this. And we can put glass slides to use for our measurements on the other tools that we have. After it goes in there, we can do a little bit of a argon sputter etch to clean off the wafer of any oxides. Then we can choose to deposit which one of the metals that we want for a certain amount of time, and that will determine the thickness of the niobium deposited. This is our NAG sputterer, MRC 902. And this one just has two different metals. Right now it has copper and titanium, which we're using for some of our resistor experiments. This is an old evaporator that we have that we can deposit layers of titanium and mostly indium in this system. It works by using electrons to melt metals in a crucible like this to the point where they are evaporated and it kind of floats up onto the wafer that's above them. So you get a very thin layer that's more evenly dispersed. And you have these little metal pellets that go into the crucible, and they're melted when they're hit with a beam of high energy electrons. This is a PCVD tool we use to deposit silicon nitride. And that is used as an insulator to protect your resistors and your wires from interfering with each other. It also has an added benefit of being clear, so you can see through it to see all of your features underneath. We have lines here for our gases that come in. We have silane, ammonia, argon, nitrogen, hydrogen that go into the tool, and these are the exhausts that go out, which are then sent to a scrubber, cleans them before they're released to the atmosphere. This is the CHA evaporator. We use this tool for our titanium, gold, palladium depositions. It has a carousel on top, so it can do up to 9 wafers at once. You can see here we have some dummy wafers that'll have different layers of metals on them, which we can then use to get the right resistances that we're looking for. Coolest machine, I think this one, because it's evaporating things like gold, metal, titanium, stuff you don't normally get to play with in your everyday life.
This is a Kurt J. Lesker Luminos DC sputtering tool. We use this 4 4-inch targets, interchangeable. We right now use it to the DC sputter hafnium, niobium, titanium, molybdenum. Yeah, hi, I'm John Vivaldo. I'm a senior process engineer here. Been here for quite a long time. This will open up, an arm will come out. We'll load a 150 millimeter wafer on the arm. The arm will bring it back in, rotate, deliver the wafer into the chamber, and then we run whatever the recipe happens to be, or whatever you want to sputter. This is another tool made by Kurt J. Lesker. It's a DC sputtering tool similar to the other tool. And this tool we use exclusively to make the Josephson junction. It's one of the primary features in the superconductor industry. So that's all done exclusively in this tool. This is actually the coolest machine for me. It's a completely manual tool. I enjoy running it. It has a lot of valves and everything you need to manipulate to get the desired results that you like. Sometimes it's a lot funner than just kind of pressing a start and hang out. Here you have to manipulate everything in the correct order to get the desired results. So I enjoy this machine. I enjoy working on it. This is the latest addition to the fab. It's a deep silicon etcher. Basically, it's used to we use it to etch vias through the silicon, so we can access the back side of the wafer. We're hoping at some point in time to have metrology and circuits on both sides of the wafer. These are all the chases where we keep all our gases. So all the tools, whether it be the ride tools, the sputtering tools, the evaporators, they all need different gases. So this is a gas farm. We have argons, oxygen, nitrogen, helium, nitrous oxide, SF6, CHF3, whatever gases we need are here. This is a plasma lab. 3 of the tools here are used for etching. One of the tools is used for deposition. These tools are reactive ion etchers used for etching. This is a metals tool. We etch molybdenum, niobium, titanium, tantalum. That's all done in this tool. We use sulfur hexafluoride, SF6 or CF4 to etch all the metals here. This tool is an inductively coupled plasma etcher. We use chlorine, boron trichloride. We use it to etch niobium, aluminum. That's all done in this tool. The last tool in this lab is the Plasma Enhanced Chemical Vapor Deposition tool, again by Samco. It's a single wafer. The chamber opens up, you load the wafer in, and it uses TEOS, tetraethioxysilane, and oxygen to deposit an oxide on your wafer surface. It's very conformal.
Hey Mario,
Hi.
what do we got here?
So here is a chemical mechanical polishing machine, and what it does is it smoothens and flattens a layer of our wafers so that we could add more complexity to our chips. A wafer is held by vacuum by that polishing head there, and a slurry, which is a chemical mixture dispersed with nanoparticles, is put onto that pad there, and the polishing head applies mechanical force and combined with that slurry to smoothen out and flatten that surface. The most fun part is to see the results in that dilution refrigerator after everything's said and done. My name is Mario Ranzulo, and I am the Senior Process Engineer here at SEEQ.
How are you?
Yeah, this is a box. I'm going to start putting wafers in there. I'm going to start processing wafers. This is the first step where you need this kind of boxes to go back and forth from different labs. I'm Daniel Johannes. I am the fab lead here at SEEQ. So this is our lithography room where we do all the lithography steps. So myself and Mark will work on this area.
Hey, Mark.
Yeah. Hi. So all the systems here we see they use UV light to basically expose this pattern that we have, this different pattern that you see in here, and translate these patterns into the resist. This machine is the one that we first put the resist on in one of these chambers here, and then some baking chambers here. So once it puts the resist in there, so this one is 1-to-1. Basically, whatever you see here will be directly printed onto a wafer. And then we have this one, which is 5 times reduced in size and exposed into wafer. So using that machine that you see over there. Mark is working on the stepper. This is a 5x reduction stepper where you saw this mask over there. So it basically sends UV light, like a deep UV light through the mask. Wherever it's not exposed, goes through the mask and exposes the wafer. Yes, that's a 6-inch wafer, 150 millimeter wafer. Yeah, so that's the size. You can see, as you can see here, like those are the different patterns that are basically. In this one, we have 3 different masks that are being printed.
First, we design our chips, and then we manufacture them in-house in our fabrication facility across the street. Then those chips, after being manufactured, are being diced and then being brought here. And here, this lab will have 3 different temperatures, 3 different platforms at which we can test. 4 Kelvin, we'll just dunk it in liquid helium in next door lab. This is 100 millikelvin, and we have also dilution refrigerators of 10 millikelvin or so in the next lab. Those are dilution refrigerators. Both of them are cold right now, and temperature of the sample stage right now of this one is slightly more than 8 millikelvin. Slightly more than 8 millikelvin. Yes, we have current sources here also. We have digitizers, we have amplifiers, we have mixers. Everything here in this like PXI chassis here, and it's also being remotely controlled. One of those modules, it's nothing more, nothing less, just that's a computer, portable computer, which controls everything inside here. And this is wires are being run to this dilution refrigerator down to millikelvin temperatures. Here we're testing our 5-qubit quantum computer, which is being tested right now, again, remotely by people. And all these tests are being run from England. So again, like I mentioned a few minutes ago, chips were fabricated across the street, and then they're brought here already diced. And usually we have chips in different form factor, either 5 by 5 millimeter chips, which are smaller, or 10 by 10 millimeter chips, which are bigger chips. And for these different chips, we have different packages, different probes, immersion probes, and different packages for millikelvin. For me, at least, I mean, a lot of things here, it's pretty cool. For example, this dilution refrigerator. When I started my career, it was like quite a long time ago. These machines were pretty difficult to operate, and it was just fuse those machines in the wall. Now those machines are pretty standard, so they just call refrigerators in them. So basically people buy them, Delivery time is kind of not one day, not few days, maybe a few months. But after they delivered, you could plug them in, press the button, and let's say 24 hours, 30 hours or later, you have like millikelvin temperature, close to absolute zero, which is still kind of, you know. I'm Igor Wernick. I'm Director of Testing and Development, and I lead all measurements here at SEEQ at Ulster.
How you doing? I'm doing our 4 Kelvin testing in liquid helium right now. So I'm controlling our equipment and our hardware, which you see behind me here, and those are connected to our shield room. And inside of the shield room here, we have one of our 4 Kelvin wet probes, and it is dunked into our dewar of liquid helium here. Upside down, it's all the way, the chip is all the way in the bottom, and these are our room temp connections up here on the top. My name is Jason Walter. I'm a senior engineer, testing and design. Been here for about 7 years now. There we go. So this is our 4-output switch control demultiplexer, in which I am addressing each of these 4 outputs by turning my 2 switches in a state of either 00, 10, 01, or 11 to address each of the outputs in series here. So when I address each output in turn, I expect to have my input clock pass through to the appropriate output, which is what I see here with each output in turn triggering and none of the other outputs triggering when they're not supposed to. So this is a good working circuit, which we are then planning to use this physical carrier chip to bond with one of our quantum chips to make a multi-chip module. So I'm pre-screening at 4 Kelvin right now to make sure that our SFQ circuitry, control circuitry works correctly for further testing at millikelvin and to have it talk to our quantum chips. This is our large bottom chip that has all of our SFQ control circuitry, and then we take a smaller flip chip that has our qubits and quantum circuits on it, and we physically put them together, squeeze them together with specific lines so they can communicate and be magnetically coupled. And then by only accessing our control circuitry, we can communicate and modulate and set our the qubits, the quantum circuitry, without physically directly talking or communicating with the qubits themselves. Only the control circuitry. That's our final goal, right? Is to have everything be controlled by our SFQ control circuitry, and not have to control each of the qubits individually.
That was an amazing lab tour. Thank you so much, John, Katie, and everyone else involved in the team for creating this. It really gave a detailed view into the kitchen. Actually, there are some comments on Discord that this was a very advanced kitchen with many flavors. Thank you for showing the fabrication in such detail, all the steps that need to be taken. Fantastic. There are a variety of questions. First, John, could you share about what does it take to get to a foundry from academic level to what you established?
Yeah, so first off, let's just think about what a foundry is. So there are lots of academic groups around the world that have the ability to fabricate chips. Usually they're on very small wafers, and the goal of them is to further research. Then at the other end, there are companies like TSMC or Intel or Samsung or whatever that are making AMD, that are making, you know, huge, they're on 300 millimeter wafers, high throughput, fully robotic systems. They're incredible technologies for miniaturization, have extraordinarily good process control and yield. We are in between those two. So we've built what I want to call a development stage foundry, where we are taking our mature processes, which we're constantly evolving, and we're applying them to all the designs our designers are coming up with based on the test results that we get. And so the key for us is in having fast iteration of design, manufacture, test, and then feedback. And so really, that's really the nature of our foundry, is to really make it a development stage foundry. It will work on a commercial basis for sure. And we commercially manufacture chips for NASA, the Department of Energy, the Department of Defense, NIST, and other groups around the world.
I have added Madalena as well. She is a researcher in trapped ion technology to aid with the Q&A. Katie, next question was in the beginning of the lab tour where a chip was shown, and Mohammed Reza from Iran asks, why those particular patterns? Can you comment a bit on the chip?
So I think Caleb was mainly describing the quantum layer. So this is the layer from which we have our transmons. So there's a series of commonly seen features in the blurred out images you were looking at. The circular feature was the design orientation for our superconducting qubit that we were using in that test iteration. The wiggly lines, they actually just represent resonators. Resonators are just lengths of superconducting material, and they're sort of like the middleman. They enable us to read out the state of our qubits. So that's typically you see circular things and wiggly lines. They're just qubits and readout systems as a grand tour.
Great, very clear. Over to you for the next question, Madalena. Oh, it seems she cannot unmute yet, so I will continue. A question by Paulina. Thank you for the informative tour. Can you share what class is the clean room and how large is the team that manages the clean room?
So it's hard to get a sense of it. And by the way, I want to thank Frederick Karlstrom for making this video. He was really, really instrumental in making this happen, and he did a great job. One of the things that's hard to grasp unless you're in the facility is that we have several clean rooms. We have clean rooms that are for lithography, for etch, for CMP, we have multiple clean rooms, and each one of them has different standards according to the classification. So they are among, so some of them, for example, are really, I mean, they are as good as, maybe not as good as you can get for some of the, for like what TSMC would require, but they meet a very high standard. And some of them are, you can walk in, you still have to be dressed and everything, but you don't have to wear a certain kind of clothing. You don't have to get your shoes, changed, or, things like this. So it's really a range of clean rooms. And again, I mean, they are physically different rooms. So you saw people going down hallways, from room to room there. So a lot of foundries have like, one big facility, it's, centralized and all that. This is not built that way.
Thank you. Over to Madalena.
Hi, thank you so much for the talk and the lab tour. A question here is about the chips. So how do your chips compared to the DWave chips that are used for quantum simulations?
Well, DWave, and Katie, you can maybe weigh in on this one as well, but DWave are really working on quantum annealing, not so much gate-based quantum computing. And so the nature of what they're doing is fundamentally different from what we're doing. Now, I know there's some discussion around DWave. They've mentioned that they're trying to build gate-based quantum computers too, but,
Yeah, DWave work on simulating Ising model problems, which problems like traveling salesperson problems. Their qubits are a little bit different in flavor because although they are superconducting qubits as well, in order to encode these types of problems, they have to be tunable in 2 dimensions, both X and Z tunable. So their sort of layout is very different to our qubits. However, the processes for fabricating the aluminium junction qubits that they now specialize in is similar to us. So, DWave could one day say, we want to do gate-based operations rather than, Ising problem issues, and then ask us, can you help out with our driving? So we tackle different problems, but, there could be a relationship there as well.
That is right. And DWave is actually working on both indeed. On Thursday, we will have Alex Kosigi from DWave to present everything. So everyone, then we should ask this question again.
Yeah.
Artem from Mexico asks, when will the SEEQ technology be available as a cloud service? And through what cloud provider?
Yeah. So by the way, I just want to do a shout out because I'm just thinking about it. One of the things we didn't cover to Katie, that during COVID, we had a big frustration that everybody was shut in, but our chip foundry and our testing facilities, our chip foundry was open every day. We never missed a day. And our testing was available sporadically. And Katie built a network-based system that enabled us to do remote testing so that we could actually do testing from people's houses into our lab, et cetera. And so we sort of got this idea, oh, this is pretty good. And then we brought on somebody else to work with us on building out a cloud-based system to be able to support SEEQ System Red. Again, our business model is really less around building full systems that are going to be available to third parties over the cloud than in partnering with large companies in particular, but even some startups, on embedding our technology into theirs to help them scale and to support all the functions that we can bring. So more of the cloud work that we have is really internal for us, both for testing and for, well, Katie, do you want to talk a little bit about, like the quantum, the control core and bring, qubit, automated qubit bring up and all that kind of stuff?
Yeah, and please share more your role and work too, Katie.
Yeah, sure. So in terms of us operating as a cloud service, we have brought up multiple qubit systems and then ran a series of algorithms on them remotely that's been deployed remotely via a web application that's been done in SEEQ already, which is good. It's not quite our main focus right now, but it's something we've actually already done. Good news, so big tick. In terms of other things like automation of qubit control, what we've been working on is finding ways to enable quantum engineers like myself to spend less time sort of bringing up the qubits and repeating measurements over and over again. So what I've been looking at doing is making automated pipelines for bringing up a qubit from no knowledge about the qubit to knowing how to calibrate, a pi pulse accurately with gate fidelity of say 99.9%. So that's two things we've worked on. So yeah, we've already done cloud deployed measurements, and we've also done sort of like cloud deployed methods for bringing up our qubits ready for algorithms as well. Both done with in-house software. This is Python based, and it's called Control Core at the moment.
Right, unless anybody has a better name for it. Yeah. But we started using tools that I think a lot of you in this meeting used, like Labber, for example. But we found that Labber was useful for a lot of things, but not for everything we did, and particularly around SFQ that we're supporting. That we need to be able to support SFQ, and so that we built SFQ support into Control Core, among other things, I would say. Is there anything else, Katie, you want to mention about Control Core? Just sort of other
it's my favorite tool for measuring qubits for sure. I mean, it just goes to show how basic Python programming can really translate to doing incredible things like writing methods for tuning up qubits or encoding algorithms. It's a truly wonderful, powerful language. And I would say if you're interested in the industry, Python is a wonderful language to be picking up now.
Great, thank you for sharing. Madalena, what will be the next question?
So the next question is from Ron. Are you now working on a driver or APIs for existing quantum computing frameworks?
Katie, do you want to talk about that?
Yeah, I would say we're for sure, okay, I'm assuming the driver is the method for sending gates to our superconducting qubits. These are very much in development. We're always trying to optimize how we can improve the fidelities that our drivers yield. So improving single and two qubit gate fidelities from our SFQ drivers. That's always ongoing work. Then in parallel to that, I would say the firmware development is done in tandem with that development cycle. So I'm assuming this is the control API. Yeah, we're constantly doing iteration loops where we're optimizing how we tune up our SFQ driving and also our SFQ driving chip layout for best fidelities. Yeah.
And we're also working on making sure that we're, CASM compliant or compatible. And that's the other thing I think wasn't asked, but I think it's really important, and we were just having an internal discussion about it, is we've just developed our first generation, or I should say we've not really our first generation, but standalone compiler that works directly with our kind of architecture. And that's really, really important. I think that's an area that people don't focus on enough, frankly.
Fantastic. Then Varda from India came back to his question that he asked during the fabrication part of the lecture earlier, namely, what is inductively coupled plasma? And can you also share a reminder, Katie, for what it was used?
Oh, so I'm no fab engineer, but I'll give this question a shot. A ICP system, or inductively coupled plasma etcher, is, to my knowledge, a dry etching system which is used for cleaning chips in the process of microfabrication. What you're kind of like doing is you're using chemically reactive plasma to remove debris on your chip that's of your choosing. To get that to work, you need a system that's under a low vacuum, which is probably some of the machinery you saw at that point of the tour video. Yeah, that's what the ICP system is for.
Excellent. Next for you, Malia. Yeah.
Another question from Ron. What sort of qubit to qubit connectivity topology maps are you looking at for large arrays?
Sorry, what sort of, you sort of dropped out what sort of qubit, kinds of qubits?
No, so it's qubit to qubit connectivity
qubit to
topology
qubit
maps. Yes.
So
do
you want to, Katie, go for it.
Yeah, we're pretty open-minded about the end topology, but so far it's been, 2-qubit connectivity in series of different patterns. I mean, you can even have a linear chain of coupled superconducting qubits and have interesting results. We're quite agnostic to the sort of like topology at this point. It's algorithm dependent as to what we would design.
It's interesting you mentioned that, Katie, because one of the things that we don't talk about as much is, when I mentioned this idea about having software that supports certain verticals, is because we have a chip foundry. One of the things that we have the capability of doing is designing the kind of topology that's directly in support of a specific algorithm, so that we can actually create almost like an application-specific quantum computer. And so this is a capability that we have and that we've explored with our foundry. And so we think that sometimes there may be a particular algorithm that cuts across different application spaces, different vertical spaces, but that we can actually build a library of some of these chips. And we can also work with algorithm developers to help with the use of our kind of emulation tools, and where we can optimize some of the layouts. We can make things which reduce the requirements for qubits and for connectivity, and optimize them in a layout that we can manufacture and support.
Then a very different question from Nathan. Would you recommend a hedge fund to use quantum computing for trading?
So without getting into too much, We've had conversations with such groups. There are even investors that are involved in our company that are very interested in the answer to that question.
I can understand. And Madelina, what's next?
A little bit about the lab equipment that you're using, how difficult it is to acquire it. And do you make any yourself, or do you need to make any customizations to what you buy to use it for your purposes?
Yeah, so first off, nearly everything there is you could buy, right? However, I will tell you that we have made a lot of customization of what's there. So the equipment we use and the process we use is actually well known from the CMOS world. But because we're not putting down transistors and we're bringing up just some junctions as an example, because we're using materials like niobium and tantalum, because even we can work with sapphire wafers and all kinds of things, it makes it we have to make modifications to some of this equipment. Some of it's quite special, a lot of it's very specialized, but you could acquire this. There is tremendous know-how in this process. It's one thing to buy equipment and even build a team, but to really make a chip foundry work, it takes years of real integration and a team and a process that you get really good control over. And it's, this chip foundry has been operating for over really close to 30 years. So it's evolved to exactly what we need.
Coming to a last question. We talked a lot about energy efficiency. Valerie asks, do you have a platform or system for efficiency measurement post-fab, testing the energy rating for the chip and onboard operations?
Yeah, so that's a great question. We're working on that and trying to make sure that we understand exactly what the requirements are and what we're working on. I mean, look, I'll just show you an example. So this is, I don't know if you can see it. Let's see if you can see. Well, you can sort of see it. Kind of a bad background. Sorry. This is one of our chips. This is a multi-chip module that has, most of the functionality of a quantum computer, right? So we can measure this and we'll look at what it takes to run this. And typically it's incredibly low level energy, but you need to be able to look at the entire system. And so we've been working with some groups on trying to do that, to see if we can create some equivalency of our system and kind of everything else that's out there. But it's of really high concern to us. And as I say, energy, I always like to say energy efficiency is in our name, SEEQ, Scalable Energy Efficient Quantum Computing. So it's central to what we do. So we need to be able to quantify it and show and demonstrate how this will scale from an energy perspective.
Would you both like to share some less advice, Katie in general and John, for prospective entrepreneurs in the quantum space? Some less advice to everyone.
Katie, you go for it first.
I'm not so good at entrepreneurship, but perhaps from the perspective, getting involved as an engineer, I would say internships, summer schools, summer projects are excellent ways to find yourself in this industry. Any opportunity you have to get inside of a lab, take. Any opportunity you have to pair program with an algorithm developer, take. I think that was really how I personally fell into this field, and I'm very grateful of that.
Yeah, and I would say that to think about from an entrepreneurial perspective, I think it's really important to have high-level kind of mission goals that help inform what you're doing and making sure that that what you're doing really, kind of makes sense and everything. But I think it's in our area, it's easy to be seduced by a novel technology and harder to develop really compelling business models. And it may seem like just because you have developed a better widget, a better component, a better technology, a better process, etc., may not mean that you actually have developed a good and fundable and sustainable business. And so really thinking through things from a business perspective to understand who your market is, what problems you're solving, the value you're creating, what's distinctive, what's protectable, how much it's going to cost to fund the thing you're doing, who can be the proof points, what are early proof points, etc., to make sure that what you're working on has some staying power and some depth. Because it's easy, and particularly we're seeing in the quantum space, lots and lots of academic groups will have like a good idea. I mean, a really good idea. I mean, I don't mean to, to diss it or anything. It's a great, great ideas, but it doesn't necessarily mean it's a business. It doesn't necessarily mean that it's a fundable proposition. And so really think about that hard, and maybe even think about how are there other ways to bring this to market? Could you license it? Could you team? Could you create joint ventures? Other methods to leverage the important work that you're doing.
John, Katie, thank you very much for this great session. Wonderful advice and fantastic lecture. It was really a pleasure having you, really inspiring. Thank you very much.